All right, let's look at this now. This is a topic we're going to discuss for the rest of the semester. The sooner you memorize these, learn these, the easier it'll be for you later on. This sheet here is called the Library of Functions. These are a list of all the functions that we'll be using in this course, and we're going to discuss, once looking at the function, what the graph is going to look like, or if I see the graph, what the function is going to be. This will help us calculate all sorts of things later on. It'll help us do transformations if we have larger equations. So let's begin. A constant equation. If y equals a constant number, let's say 2. Let's say that we have an equation y equals 2. That means no matter what x you give me, y is always going to equal 2. And notice there's no x value here, so it can't cross the x-axis either. So what this graph looks like is a horizontal line through whatever y equals. If it's -4, it'll be crossed this way. If it's 5, it'll be up here. But it's a horizontal line. We know here, since it's a horizontal line, the slope is 0. The domain. The domain represents the x values of this graph. What are all the possible x values? Well, it goes all the way to the left to negative infinity, to all the way to the right to positive infinity. So it's everything from negative infinity to positive infinity. The range is how far it goes up and down. Here's the y-axis. So it only goes through 2. So the range is that value there. And later on we're going to discuss whether it's brackets or parentheses. All right, so that's a constant function. It's a horizontal line. Now let's do linear equations. A linear equation defines a line. We know it's a linear equation because x or y, neither of them have any exponents, radicals, or they're not denominators. They're not 1 over x. So that's how we know it's a linear equation. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 2. When x is 3, y is 3. When x is -1, y is -1. So it's, you see that this line is growing. Like that. So now what happens here is this line can go up or down or change directions. It can be a negative slope or a positive slope. The domain of this function, looking at the negative x, the graph keeps on going forever and ever. So it goes from negative infinity all the way to positive infinity. It keeps on going. And the range, it keeps on going down, 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 down. So it goes from negative infinity and it keeps on getting up. So it's positive. So that one likewise is negative infinity to positive infinity. So whenever you see a linear equation, you know automatically that the domain and range are infinity, both of them. Instead of writing negative to positive infinity, a lot of times we simply use that r. It means all real numbers. All right? Now on this side, absolute value of x. What the absolute value of x represents is no matter what you put inside there, if you put a positive number, it's positive. If you put a 0, it's 0. And if you put a negative, it comes out positive. So in other words, what this one tells us is y can never be negative. So when x is 0, y is 0. Absolute value of 1 when x is 1 is 1. If x is 2, absolute value of 2 is 2. When x is 3, absolute value of 3 is 3. So the positive side looks like this. It keeps on going. The negative side, if I put negative 1, the absolute value of negative 1 is positive 1. So the absolute value of negative 1 is positive 1. The absolute value of negative 2 is positive 2. Absolute value of negative 3 is 3. So this side goes like this forever and ever and ever. So it goes, x goes to negative infinity and positive infinity. So the domain is negative infinity, positive infinity. The range, can it be negative? No, there's no negatives. Can it be 0? Yes, so I can start at 0. And I can use it, so I put a bracket. And then it goes up, the graphs keep on going up higher, so it goes to positive infinity. That's an absolute value equation. Basically what it says is, it's the same graph as this, but instead of the negatives, I take that part of the graph, make it all positive. So now I have the absolute value. Let's look at quadratics. Once an exponent exists on your variable, it is no longer a straight line, it's now a curve. The way this graph looks like is when x is 0, y is 0. Let's make it a little table. So when x is 0, y is 0. When x is 1, y is 1. When x is 2, 2 squared is 4. When x is 3, 3 squared is 9. So it goes all the way up here. So it's a curve. It's not a straight line, it's a curve. Likewise now in the negatives. When you square something, negative 1. Negative 1 times negative 1 is positive 1. Negative 2. Negative 2 times negative 2 is positive 4. Negative 3. Negative 3 times negative 3 is positive 9. So this side is a curve also. We see that there are mirrors. Here's the bottom point, call it the vertex. So if we go 1 to both sides, they both go 1. If we go 2, they both go 4. If we go both to 3, so it's a mirror image. The domain, I can use any x I want to, plug it in there. So negative infinity to positive infinity. The range, the smallest it can be is 0. And I can use that. And then it goes up to infinity. Radicals. Radicals are the opposite of squares. If you ever want to get rid of a square, square root it. They'll cancel each other out. So the only rule we have is x inside the radical cannot be negative. For example, if we had square root of 4, we know that equals 2 because 2 times 2 equals 4, and there's 2 of a kind, so that's it. Square root of 25 is 5 because 5 times 5 is 25. There's 2 of them. Once we have 2 of them, we take it out. So this is a square. Square means 2. So we need 2 of a kind to take it out of the radical. So you can't put a negative in there, because if I put negative 4, I can't use negative 2 and negative 2. Negative is positive. so it'll never be negative. So we can't use negative. We can use 0. Square root of 0 is 0. Square root of 1, yeah, 1 times 1 is 1. Square root of 4 is 2. Square root of 9 is 3. So we have a slight curve here. The domain starts at 0, goes to positive infinity. I can use 0. The range starts at 0, and it keeps on slowly going higher, so it goes to infinity. So if you can use the number, we put a bracket. If you can't, we can never get to infinity, so we put a parenthesis. Cubic. Now remember, when you have a square, it's negative 1 times negative 1 is positive 1. Negative 2 times negative 2 is positive 4. But when we have an odd exponent, negative 1 times negative 1 is positive 1, times negative 1 is negative 1. Negative 2 times negative 2 times negative 2. 1, 2, there's 3 negatives, so the answer is negative. 2, 4, 8. So it's negative 8. Likewise with the positives. When x is 0, y is obviously 0. When x is 1, 1 times 1 times 1 is positive 1. 2 times 2 is 4, times 2 is 8. So if the input's positive, the output's positive. If the input's negative, output's negative. So let's look what that looks like. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 8. Way up here. So you see at x is 2 here, it goes to 4. This one goes to 8, so it grows a lot faster. Likewise, negative 1 is negative 1. Negative 2 is negative 8. So there's that graph. The domain of a cubic function, x can go to negative infinity. It keeps on going. It goes to positive infinity. So it's negative to positive infinity. Likewise, the range keeps on going down to negative infinity or up to positive infinity. Notice how the square root, the quadratic, the square root, the square number, and the cubic, they both have a direction. The radicals now are turned over on a side. Now we just go backwards. In this one, I put in the 8, negative 8. If I put negative 8, the cube root, I need 3 of a kind. 8 is made up of 2 times 2 times 2. There's 3 of them. So the answer is negative 2. Okay, so when x is negative 8, it's negative 2. When x is negative 1, the cube root is negative 1. When x is 0, when x is 1, cube root of 1 is 1. When x is 8, 8 is made up of 2 times 2 times 2. So this one, see the root functions. This is called the root. There's an invisible 2 here for the square root, and there's a 3. What that tells us, for square root, we need 2 of a kind. For cube root, we need 3 of a kind. For example, cube root of 8 is 2, because 8 is made up of 2 times 2 times 2. There's 3 of those. Once I have 3 of a kind, I take it outside the... I'm sorry. 8, there's 2 times 2 is 4 times 2 is 8. Once I have 3 of a kind, I take it out. That's how roots work. The domain obviously goes to negative infinity and positive infinity. And the range, again, it's slowly going up and down. So it's also negative infinity to positive infinity. Now, before going any further to the next page, let's look at these. If this is x cubed, this is x squared, this is x. So what's the exponent here? 3, 2, 1. The exponent tells us a lot. It tells us how many times we can cross the x-axis. Linear only crosses once. The quadratic, if it's further down, I can cross it 2 times. The cubic, it could exaggerate, I can cross it 3 times. But there's something else we notice. If the exponent is odd, 1 and 3, look at the end of the graphs. They're pointing different directions. If it's even, then both ends point the same direction. So these are the kind of things I want you to start noticing. If it's an odd, the opposite direction. If it's even, it goes one direction. Okay, exponentials. For this one, we have to have b being greater than 1. Because if it equals to 1, then 1 to any power is 1. And you cannot have negatives because it makes it a fraction and it just bounces up and down. So what this says now, no matter what x is, if it's negative, let's say b is 2. So we have 2 to the power x. Notice our exponent is our variable. When x is negative, let's say x is negative 3. That negative on the exponent doesn't make the answer negative, it makes it a fraction. And we'll prove this later on, but right now, that's what it means. So it's always going to be positive. That's the kind of the graph of this one. Starts out low, always goes through 1, and it keeps on going. It never crosses the x-axis. So at this point, since it never crosses the x-axis, that's called an asymptote. An asymptote is a line that the graph gets infinitely close but never touches. So the domain of this, the x's can go infinitely and it'll keep on going. So it's negative infinity to positive infinity. The range, since we don't have an x-intercept, y gets very, very close to being 0. So we say it starts at 0 and it goes up to infinity, but it doesn't touch it. So it's a parenthesis. Similar to the last page when we looked at the cube root and the cubic function, they're just rotates of each other. Same thing with the logarithmic function. With the base, this is the base. If it's greater than 1, the graph will it'll cross 1 on the x. This one crossed 1 on the y. This one crosses 1 on the x. And it looks like this. So it's the same as this graph. It's just that if you took the graph and just folded it across the 45-degree line, you get this axis, this graph. So the domain, it gets infinitely close to 0, but doesn't touch it. And it goes on to infinity. So that's where we use parentheses. It gets very, very, very close to 0, never touches it, so it doesn't cross. The range goes from negative infinity and all the way up to positive infinity. These are perfect examples of inverse functions. The domain of this one is the range of this one. The range of this one is the domain of that one. Those are what we call inverse functions. That'll come next chapter. Now, inverse functions, it means 1 over x. X is now on the bottom. Again, this is a special operation, so it's not going to be a straight line. It's going to be a curve. What we have to remember here is this. The bigger the bottom number gets, the smaller the number. So 1 over 1 is 1. So when x is 1, 1 over 1 is 1. When x is 2, so it's 1 over 2 is 0.5, so it's half. When x is 10, that's 1 over 10, that's 0.1. That's very, very... So this half of the graph goes down infinitely close to that asymptote. So just the opposite now. If my x's are fractions, like 1 over 1/2 equals 2. 1 over 1/4 equals 4. So this half of the graph looks like this. Again, that's another asymptote because it never crosses it. But same thing on the left side. If I put a -1 in there, 1 over -1 is -1. 1 over -2 is -1/2. 1 over -10, -1/10. So this half of the graph looks like that. And 1 over -1/2 is -2. And so on and so forth. So that's the inverse function. These are asymptotes. Asymptotes are where the function's undefined. You cannot, x cannot equal 0 because it's undefined. That is an asymptote. It's the x value where the function is undefined. It means the graph can't cross it. Likewise, the only way a fraction can be 0 is if the top number is 0. If the top number is 1, it'll never be 0. So y will never be 0, never have an intercept. So the domain here, x goes from -infinity very close to 0. Then it starts over here, very close to 0 to positive infinity. And we put a union symbol. That means the answer could be here or it could be here. That's what that means. It's like an or statement. Likewise for the range. It can go from -infinity awfully close to 0. It never touches 0. Then it starts on the other side of 0 and goes up. So from 0 to infinity. Since it never touches 0, we put a parenthesis there. And we put a union. Because if I think of an answer, it could be here or it could be here. So So that's 1 over x. So 1 over x squared, two things we notice, three things. Since the top can never be 0, it has an asymptote. So since y can never be 0, because the top can never be 0, again, then this bottom, x cannot be 0. That's another asymptote. And y can never be negative. Y is always going to be greater than 0. Why? Because you squared x. Anytime you square a negative, it becomes positive. So when x is 1, we have 1. When x is 2, that becomes 1 over 4. It goes down here. When x is 3, that's 1 over 9. So again, this side here goes much faster down. And if it's between 0 and 1, it grows much faster this way. Remember, but it doesn't ever touch the y-axis. Nope, it can never be 0, be negative, so it can't be there. It has to be positive. If x is negative 1, negative 1 squared is positive 1, so it's 1. So this half of the graph looks like this. If you think about it, it looks like the Atari symbol. The domain here, again, it starts at negative infinity, gets very close to 0, but doesn't touch it. Doesn't touch 0, but it starts right after it. So it starts at just after 0, and it goes to positive infinity. And we union it. That's the domain. The range, it can't be negative. It can't be 0. So it starts right after 0, and it goes up to infinity. And the last one we're going to talk about for this sheet is called the greatest integer function. In programming, we use int. That stands for integer, x. The symbol here is just a big parenthesis with another line. Another bracket with another line. So what that means, integers are numbers. 1, 2, 3, 4, negative 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. So what that means is, if you see this, everything after the decimal, just cut it off. So when x is 0, y is 0. X is 0.1, drop off the 0.1, so it's 0. X is 0.5, drop off the 0.5, it's still 0. It goes all the way to 1.0, it jumps to 1. It does the same thing, 1.1, 1.2. All the way to 2.0, it jumps to 2. When it gets to 3.0, it jumps to 3. And 4, it jumps to 4. And likewise down here. At negative 1, and so at negative 1.4, it drops down to negative 2. Negative 2.6, it drops down to negative 3, and so on and so forth. This is called the stair-stepper function, because it looks like a bunch of stairs. The domain, it keeps on going forever and ever, and I never miss a number, so it goes from negative infinity to positive infinity. Even though it's not continuous, it doesn't miss a number. The range, on the other hand, all the integers, the 1, 2, 3, negative 1, 2, 3. So those are the library of functions. Try to start memorizing. When you see the function, you know what the graph looks like, and vice versa. If you see the graph, you know what function it corresponds to. If you see this picture, you know it's 1 over x. If you see the Atari, it's 1 over x squared. All right, so start putting that to memory, and let's talk about inequalities now. All right, thank you.